Hello everyone, today I will do a relatively short explanation about black holes, tidal forces, and why the more massive black holes are less dangerous all the way up to supermassive black holes, which are, at least in this specific way, relatively harmless. I will keep that relatively short because it's a rather specific topic, and I will then split that up more or less in later videos talking more about tidal forces unrelated to black holes, and maybe also more about black holes unrelated to tidal forces. And if there's interest, I might also talk about the movie Interstellar and some of its very big issues, if there's a bit of interest, because generally I don't really like ripping apart something that sucks when instead I could be talking about something that's actually worthwhile and good. Although in my very next video I will be stepping away from theoretical physics and black holes again and talk about actual spaceflight optimization and current progress. Also, another little announcement. Today, in about 12 hours, a Soyuz rocket will launch 3 astronauts to the International Space Station, which I will livestream, while the Ariane 5 launch that was also scheduled for today has been delayed. But for now, let's talk about black holes and why the more massive ones are in a way less dangerous. And I'll keep it rather simple, and that is possible because we're talking about a proportional relation here, not about the actual numbers, and that's quite interesting that in black holes the more complicated mathematics actually only add a sort of constant factor to these calculations, while the proportionality, or how the result changes when you change the black hole, is relatively simple to understand. But first of all, I'll do a very short recap on tidal forces and what they actually are. So the thing is that if you're free falling in space without measurable friction or a ground to stand on, the gravitational forces of Earth or any other body nearby will basically affect every single atom in your body equally, and that is why you feel weightless. You're in free fall and there is no net force between them that would deform your body or hurt you in any way, as all these atoms essentially fall alongside each other at an equal rate. Of course, that gets a bit more obvious if you go to the relativistic definition of gravity, where space-time itself is deformed so that everything moves along with space-time towards an object with mass. However, we actually don't really need relativity for this explanation, as it too only adds a constant factor rather than any additional relation to this problem, so don't worry, I will mention relativity, but the math we will be doing doesn't actually require it. Now, tidal forces are the relative forces between the parts of one body which are caused by the difference in distance to other bodies. I have previously already made a video explaining tidal forces themselves and a few examples like the effect of moons in a bit more detail, and there are plenty more or less complicated examples for them, but essentially the idea is that if, for example, you are in Earth orbit, and while there is no up and down in space, we can say for this explanation's simplicity's sake that you're floating around with your feet towards the Earth and your head pointed away from the Earth, then while your entire body is affected by the Earth's gravity and your trajectory can be approximated with a Kepler orbit, there is an effect that your feet are closer to the Earth than your head, and thus your feet get a slightly stronger gravitational pull than your head, and you feel like you're basically being pulled apart. Now, this effect is relatively weak because compared to the Earth or the radius of your orbit, you are relatively small, and gravitational force of the Earth is generally in a range that we can survive, obviously. If you are in a low Earth orbit, you might be around 7 million meters away from the center of the Earth. If we round your height to 2 meters, that means that your feet are only 3.5 millionth closer to Earth than your head, and since it's a square function, that gets doubled again, but that still means that your feet only less than 1 millionth more gravity than your head. However, if you get close to a black hole or a similar very massive dense object, then this might be different. For once, the smaller an object is, the closer you can get to it, and the closer you get to an object, the greater the percentual difference gets. If we imagine a tiny planet with a radius of 2 meters and you're standing on it, then your head is twice as far away from it as your feet, and your feet experience 4 times as much gravitational force, whereas for a large object like the Earth, it's again only a difference of millionths. And on the other hand, of course, a black hole generally has a very strong gravitational pull, so 1% of that gravitational pull is a lot more of 1% of Earth's gravity. So if you approach a black hole, not actually even entering it, just flying by it, which is actually possible, you can orbit or fly by a black hole like any other massive object as long as you don't enter the event horizon, then as you fly by you might get torn apart as whatever part of you is closer to the black hole gets pulled in stronger than the part that is further away, and while your body and spaceship can freefall as long as that gravitational pull is equal on each part of it, in this situation it just gets torn apart. And this of course not only affects objects like spaceships or humans, which is anyways only an explanatory example. The idea of traveling towards a black hole is purely hypothetical. The nearest black hole is thousands of times further away than anything we can seriously imagine ourselves traveling to, and the delta V required to maneuver around a black hole can easily be a imaginary velocity several times the speed of light. But large objects like stars experience this effect very much. While getting sucked into a black hole, a star will be torn apart and elongated and basically wrapped around the black hole before actually falling in, sometimes referred to as spaghettification. And depending on the black hole, at some point even the very atoms and molecules might get torn apart, though essentially the proton within an atom's core, which is a little bit closer to the black hole, gets pulled in stronger than the proton that is a little bit further away, and so they get divided up as the closer one gets pulled in stronger than the further away one. Now, one more important thing is that we always talk about what happens when you approach a black hole and not when you actually enter it, and that's because entering a black hole is a purely mathematical concept. Time slows down as you approach a black hole, so for once you can't actually really enter it anyways, just slowly get closer and closer and closer to it but never actually reach it. And on the other hand, the events when entering a black hole become so complicated that they can only really be described mathematically. Words like entering or moving or even happening start to lose any meaning in this context. Now, the event horizon of a black hole is actually surprisingly defined based on a concept from Newtonian mechanics that we are very familiar with in spaceflight, as it comes from orbital mechanics, that is, the escape velocity. And again, we can use Newtonian mechanics here because relativity only adds a constant factor. The difference between relativity and the Newtonian approximation at the event horizon of a black hole is always the same, regardless of what type of black hole or what speed you're going at. That is simply because it is the event horizon. So we can basically still define it using Newtonian mechanics, just using a different threshold. And the event horizon of a black hole is the distance at which its Newtonian escape velocity would be equal to the speed of light. Now again, since the Newtonian model is just an approximation, due to relativistic effects, nothing can escape from the event horizon, not even light, even though it travels at its Newtonian escape velocity. Under relativistic physics, it still doesn't escape, and in fact, light is really more of an indicator here because it basically travels at the universal speed constant, but what that actually means is that space-time itself is actually ripped apart. Nothing in causality can escape from the event horizon of a black hole, until you introduce Hawking radiation, which again gets a lot more complicated and which I might also make a video about, but isn't really in today's topic, although today's topic is rather important for it, so that video would then be based upon this video. But for now, let's do the actual math and see how the mass or the radius of a black hole would influence the gravitational gradient or tidal force that you experience near the event horizon. And we can even simplify the orbital mechanics, as they also just provide a constant factor and go straight to proportionality. We know that regardless of the size of a black hole, the escape velocity at the event horizon is constant because that's how the event horizon is defined, and we can now deduce that the larger the black hole is, the less its gravitational pull at the event horizon will actually be. Its mass will still have to be greater because you're also further away from its center, but for a larger body with the same surface escape velocity, the surface gravity is actually lower, because the kinetic energy at the escape velocity is proportional to the potential energy you would need to climb up a certain percentage of the body's radius from the ground. It essentially comes back down to potential energy, with energy being a length or way multiplied by a force. We know that for a constant energy, the longer the way or the greater the size of the black hole is, the smaller the force will be, so the smaller the gravity at the event horizon will actually be. The radius of the event horizon ends up being proportional to the mass of the black hole, and with gravitational acceleration being proportional to mass divided by radius squared, that means a bigger and more massive black hole has less gravitational acceleration at its event horizon. And another factor that I had previously mentioned is that, of course, the bigger an object is, the smaller your size is as a percentage of that object's size or your distance from it. So the ratio between gravitational acceleration and tidal forces is also smaller for a bigger black hole, and in the end the tidal forces you can experience approaching a black hole's event horizon is proportional to 1 divided by that black hole's radius squared. Or since mass and radius are proportional, you might as well say 1 divided by mass squared. So a black hole with double the mass will have double the radius and 1/4 the tidal forces pulling you apart as you approach it. And based on basic human physiology and the limits of what kinds of turns jet fighters and similar vehicles are designed for, I've actually run the numbers and come to the result that a black hole with an event horizon 5 times the Earth's radius, which would be 4.2 billion times as massive as the Earth, would be just at the limit where a human at the event horizon would start passing out very quickly due to these tidal forces, whereas a black hole 15 times the Earth's radius would be relatively comfortable to approach the event horizon, apart from the psychological aspect that you will never leave again, while a black hole with about half the Earth's radius would be instantly lethal if you approached the event horizon, since the tidal force difference between your center of mass and your head would be as large as the acceleration, which in crash tests is usually considered an instant kill. Of course, these similar effects also apply to any other massive dense body. It doesn't necessarily have to be a black hole. Obviously, a smaller object with less mass could be just as dangerous if we imagine that a black hole with a radius half that of Earth would kill you before you reach it, then a black hole with a radius much less than 1/2 the Earth's radius would kill you long before you actually reach it, which means that an object that is the same mass but slightly bigger than that black hole could also kill you while not being a black hole. However, due to the physics of their formation, black holes are basically the densest objects that there can be, and thus the objects we're talking about these effects makes the most sense. So with this I will end my little explanation of spaghettification and why bigger black holes are in a way less dangerous than smaller ones. For now, my next video should again be about the slightly more practical topic of rocket design and optimization, and I will later again return to explaining more theoretical stuff like this. For now, if you have any questions, be it physics, spaceflight or aviation related, I'm always open for requests, and as always, thanks for watching.